So as we stop here, let's take the time to discuss our paper, and if we have any questions about it. This paper is it's a paper from a while back, about 5-6 years ago, but it does talk about some things that I think are interesting. One is that we were talking about square wave voltammetry previously, so we can think about square wave voltammetry using it in a real system. So does anybody have any particular questions about this paper and the results they talked about?
What do they mean about the anodic stripping?
Yeah, we have never talked about that. It's we will talk about it a little later, but let's give you a brief idea. Anodic stripping voltammetry, or ASV. The idea is that many metals at a mercury cathode will be reduced to the metal, but then they will become dissolved in the mercury itself. So they'll form an amalgam in the metal. So zinc, cadmium, lead, many metal ions will do that. Not all, but many. And so the idea is of anodic stripping voltammetry is an analytical method. It says, let's take a dilute solution of some metal ions. If we reduce that dilute solution for a fairly long period of time, what will happen is that you have a large volume of solution and a very small mercury volume. You'll get a concentration of species in the small mercury volume. So the concentration of metal in the mercury becomes much more concentrated than it is in the solution outside that. So you may not be able to physically see, or the signal to noise ratio may be so small for trying to directly look at the current for the reduction of the metal ion. But after a certain amount of time, you've got enough in here so that the concentration is high enough so that when you oxidize the metal ion out of the mercury electrode, you get a physically large signal. So what anodic stripping voltammetry is a method they call pre-concentration. You can think about it in, if you had a bucket of a very dilute metal ions, and the idea would be the same as if you took that bucket of metal ions and you evaporated all the water away so that you were left with, say, a few microliters of liquid at the end. And then, by changing the volume factor by a factor of 1,000 or 1,000,000, you get that much increase in the concentration of your species. So the sensitivity increases by that ratio. And so you just would do an oxidation to get the metal ion. Now, if you did this with a voltammetry experiment, what you'd see when you did a stripping wave is you'd be scanning positive, so you'd see a wave that would look something like this. There'd be a peak in the signal, and the peak would be reflecting the fact that you've stripped out the metal ion, and because the metal ion, there's a finite amount in this small mercury drop, it can all be removed, rather than usually in diffusional systems we talk about semi-infinite conditions. Here we don't have a semi-infinite condition. We can actually physically remove all the metal that's in the mercury drop, and so what you see then is that you'll see a wave like this, or perhaps you might see a wave that even looks different, where you see a very sharp drop to zero when all the material is depleted in the mercury. So it's a method in general for sensitive metal determination, and it's a method that's usually very inexpensive, and it's comparable in accuracy for certain metals for things like flame ionization, or not flame ionization, but atomic absorption spectroscopy and inductively coupled plasma methods, which are much more expensive methods. So things like, people like oceanography, people that are measuring metal ions often use anionic stripping voltammetry because it's an inexpensive method and fits on a ship without too much trouble and things like that. You have to use, in this particular case, you know, you have to use a mercury cathode. You don't necessarily have to use it. You could plate the metal onto a solid metal electrode, and that you'd do essentially the same thing. You have to make sure, though, that the metal is plated in a uniform film, and then also sometimes plated metals don't really plate down as the metals. They form an oxide or something like that, and it's difficult to re-oxidize it electrochemically to see the signal. So generally, mercury is preferred for this sort of process. What's the, they're using mercury, they call them mercury ultramicroelectrodes. What's the advantage of the ultramicroelectrode in this regard?
Reduction in the IR drop.
Yeah, they do get a smaller IR drop. That's generally true. Is that really directly analytically advantageous, or what's the direct analytical advantageous result of it being small?
Current would be very small.
That's not really an advantage, is it? What's the bottom line in any chemical analysis?
Sensitivity.
Yeah.
What?
Sensitivity or
Sensitivity.
Money's the bottom line in any chemical analysis.
Okay.
All right. So no matter what anybody tells you, money is the bottom line. So, the less money you pay to do the analysis, the better. So why would this be a better analytical method in thinking about money?
Small materials.
What do they always say about time?
Oh, very much.
Time is money, right?
Yeah.
So the longer it takes to do analysis, the more money you have to spend. Some technician has to be paid, lights have to be paid. You know, you can do less analysis in any given day. So time is really not just money, but it's money cubed and quadrupled. So short analysis time is important for this particular method. So that's one of the major advantages. And so what are they doing to? So you said IR drop. That indirectly improves the time of analysis by making it. You're able to actually do a shorter analysis because you've reduced that. What else are they doing? I guess.
They say that the transport rates.
They can work in. They can work in media without supporting electrolytes.
Right. That's another advantage. They don't have to modify the sample by adding salt or anything like that, which could introduce its impurities of its own. Remember, the problem is always going to be, I have a sample, and it's not very concentrated metal in that sample, but if I add a salt, there doesn't have to be very much contamination in that metal of a salt, in that salt, because now when I do the voltammetry, I'm going to concentrate that impurity by the very nature of the result. So you don't want to add, you know, if you have to add it, you have to make very sure that it's very clean, which also adds a cost to the system. And that has to do with all kinds of things. If you add acid or something like that to the system, it's the same thing. You have to make sure your acid's very clean, or otherwise you'll have a problem.
Use that advantage here in the preparation or the use of the reference electrode. It's just they didn't like to use just a normal scalable electrode because they were afraid of some leakage. That's why they.
All right. Well, silver, a little bit of silver in the silver chloride could leak out, and
Yeah,
that,
they use the coated one containing no internal liquid electrolyte.
right.
How can you prepare something like lithium coated?
Well, I think what it is, it's a well, I'm not positive. I don't know exactly what they did, but I think the idea here is you'd have a silver wire, and you coat it with silver chloride. And if you take that silver chloride and then you dip it in a polymer solution, you'll form a coating, very thin actually compared to that, but it would be a coating of this polymer, it's so-called ion exclusion polymer. And the idea, I guess, would be that there's no internal filling solution, but the solution that's put in would actually allow ions to go in and out and solvent to go in and out. So there would be still electrical contact between those two systems that way. Yeah, so why is chloride, they were worried about chloride contamination. What's the problem with chloride contamination in this particular experiment? What happens with
cadmium or copper or lead could be deposited as chlorides, especially lead can be deposited as lead chloride.
yeah. Well, what would happen? What's the difference between mercury in the chloride solution and non-chloride containing solution? What would happen if you had voltammetry of mercury and chloride and non-chloride containing solution? Yeah, you might not be good at this, but remember the Calomel electrode is a mercury chloride system. And so chloride forms a very stable complex with mercury. And so essentially what it does is makes it easier to oxidize mercury because it can form that complex. And so that reduces the amount of anodic potential that you can apply by a significant amount. So any additional chloride in there would tend to add to a background signal. It may not be obvious that there's a direct oxidation of mercury, but you'd see an increased background as small amounts of chloride allow the oxidation of mercury to proceed. That's a problem. Why did they want to use, they made a big point of the fact that this was a iridium-based mercury ultramicroelectrode. What's the advantage of the iridium?
Yeah, this very, very low solubility.
Yeah, why? You probably don't really know. We haven't talked about this, but can you think of any reason why you'd want a low solubility of iridium? What's the advantage there?
I think they mentioned something about it doesn't form amalgams with the compounds that can interfere when it's mixed with mercury or something like that.
Well, you're probably all pretty aware that you can say if you put mercury and gold, you'll form an amalgam. That works out for almost every metal. It's any solid metal. If you put mercury on it, it'll form an amalgam. Platinum will form an amalgam. Even these noble metals Iridium is an old metal. It forms it's one of the least amalgamating materials. And so I guess the question is, why would an amalgam of platinum or mercury be a problem?
Well, they mention here that the lifetime of the amalgam of mercury with platinum or gold or silver is much shorter than it will be because of the formation of intermetallic compounds.
Yeah. Anybody know what intermetallic compounds are?
With analyte metal. Is that what does this mean? They react with the analyte itself.
Right. That's the problem with analytic stripping voltammetry. The reason is that what you want to do is, when you see these peaks coming off, they're diagnostic. So they'll strip off at different potentials depending on the redox potential of the material that you're getting. And so you want peaks at different potentials because you want to, for real samples, you might have cadmium and copper and silver, whatever in there. So you want to see different peaks. The problem is, especially since you're pre-concentrating it, now the mercury has a relatively high concentration of material in the small mercury drop. And what you can find is that things like cadmium and platinum form complexes of the metals in the mercury itself. And so what happens then is that because of that energy for that complex formation is there, it means that you don't get the stripping wave at the peak characteristic of cadmium alone. It's the peak, you get a characteristic for the cadmium platinum peak. And it turns out it had a lot of bad things. It smears the waves out. They tend to clump together into one particular point. And so a small amount of platinum won't have a problem, but if you put it on a small drop on a platinum electrode, you'll eventually see this problem. Iridium doesn't have that problem. But it actually is not just, intermetallic compounds happen for analytes that you put together in one drop. So cadmium and zinc, I think, is a good example. You get cadmium, zinc, intermetallic compounds. So if you're trying to analyze them together, you have sometimes trouble they'll stick together. What you have to do then is make sure you don't ever build up a big enough concentration in the drop to significantly form this intermetallic material. Iridium is useful for that. The big problem with iridium is it's so difficult to work with. You can't make small wires out of it. It's not ductile. It's also very hard. You can't, and it's very chemically resistant as well. So you notice how they made the electrode is kind of interesting. They started with a small wire, pretty small wire, 127 micrometers diameter, but that's not small enough. They want tens of micrometers or smaller. And then they etch the wire by immersing it in a platinum crucible containing a molten salt mixture of sodium nitrate and sodium chloride at 445 degrees centigrade. So that's quite a reactive pot of molten salt, and they have to go to that extreme to get a good etching of the iridium because it's so chemically resistant otherwise.
Is that this method is specific for certain ions, or it can determine different oxidation states for the same metal, like iron 2, iron 3, or
stripping voltammetry?
Yeah.
No, once you reduce the metal into the material, you're forming the metal as its metallic state. So you can't directly see the difference in the metal species. And what you'd have to do is do some preliminary experiments or preliminary steps to remove either the one form of the species and then do the other one, or make it so that, for example, one of the ions can't be reduced onto the mercury by setting the initial reduction potential. You can make sure that only one ion form of the ion would be reduced, and then you could strip that out, and then you could do it again with, say, both ions are reduced, and then strip that out, and then you can see by difference what the things were. Iron's not a good example because it doesn't form a good amalgam with mercury, but it'd be that would be the idea. And some ions are existing as either the free form or they might be bound up in some other complex. So you'd have to make sure that particularly for things like seawater analysis, you have to go through some chemical steps, usually involving acidifying it so that all the metal ions are present in a non-complex form that can be reduced at the same potential. Notice the square wave voltammetry. If you look on figure 3, that's the square wave voltammetry is not exactly the same as the Auster-Young square wave voltammetry, but you see the forward and reverse wave and the sum waves. You see the square, and you see that nice peak voltammogram for analysis. And now the rest of that stuff you'd not normally see, but they're showing it because they want to prove the method works, and so you're seeing more than you'd normally see. But then you can see in figure 5 the analysis for lead and copper. In this case, they're plotting anodic currents go up instead of down. That's the convention that they're following. There was another thing that they claim as an advantage, and that was they didn't have to remove oxygen from the system. And you notice that. Why would that be a problem? Why would oxygen cause problem under some conditions? Can oxygen be reduced or oxidized?
Can be reduced.
Yeah. So if we had oxygen in the system and we're applying potentials that in general are, if you notice the potentials that we're looking at there is in figure 5, they're negative potentials. So in that region we're going to see a signal in principle for the reduction of oxygen, because that's where oxygen can be reduced. And since oxygen is continuously coming in from the atmosphere from your sample cell, it's a problem unless you specifically remove it. Now, under normal circumstances, you can remove oxygen in a number of ways. And one way to do it is to bubble purified nitrogen gas through the system, or argon, or helium sometimes. And because of the solubility of gases and liquids, by adding a large excess of nitrogen, you can actually force the oxygen to come out of the system. And the problem with that is that it adds an extra step to the analysis. When you blow the oxygen or the nitrogen through the system with this gas, you can sputter up and spray off some of the sample, and that causes you may be have some error in the concentration that you eventually measure. So it's not ideal. You'd like to avoid that removal of oxygen if you can, because it makes it faster and less prone to error. So why they're talking about why they didn't remove oxygen here? Do you remember why they said they didn't need to remove it?
Well, the signals with and without removing oxygen were very similar for measuring lead and cadmium.
Yeah, if you look on figure 1, you can see there's really essentially no difference. And part of the reason for that is they've exploited the fact that oxygen tends to be somewhat sluggish electrochemically compared to some metal ions. So the reduction oxidation rate constants for metal ions, especially out of a mercury amalgam, is usually very rapid, particularly for copper and lead, cadmium and lead, copper and lead. And oxygen as slow. So what they're doing is they're making the experiment time frame fast enough so that the reduction of oxygen is kinetically slow, and so the current for that becomes very small, and you just don't see it. It's not part of the background. If you did, on the other hand, these conventional stripping voltammograms, you would see it, because usually the stripping rate is a few hundred millivolts per second or less, and that's plenty of time for oxygen to interfere with the electrochemistry. Whereas here they're doing square wave. Because we've got a small electrode, small IR drop, they can actually do high-speed frequency measurements or high-speed measurements, and that reduces the effect of oxygen on the signal. I forget what the ones in figure 1 was, but let's see, that's 150 hertz, I guess. Well, let's see.
The frequency?
Yeah.
150.
Well, I guess that's a time to stop then, so let's stop here. And, as I said, the next week we'll talk about some effect of the double layer capacitance and potential drop at the double layer on electrode kinetics.